Hello class, welcome back. Today we're talking about lecture 3, probability functions. So we finally get to do probability, and the first thing is that we want, oops, that was weird. We want a formal way of expressing probability, which I'm going to abbreviate a lot as prob, of events. So using our language that we've developed so far, events occurring, but we also want it to match our intuition. So we want to be able to use our fancy notation to say what probability is, but we also want it to match how we normally calculate probability. So let's think about some examples. So what is the probability of rolling a 2 with a dice? So this is something you would have learned a long time ago. But how can we think about it in a nice formal way? Well, what we're really doing is we're saying that a number from 0 to 1 is being associated to an event. And so the event is the event with just one outcome in it, the event with a 2 in it. And you might say it's 1/6, and that's fine. So then like later, then you learn questions like this. What is the probability of rolling an even number? And again, the answer is really just a number from 0 to 1. And it's being associated in our language to an event. And this time the event has some more stuff in it. So it'll have a 2, a 4, and a 6 in it, because those are the even numbers. Those are the even outcomes of the experiment. What about something like this? What is the probability of rolling a 1, 2, 3, 4, 5, 6? Well, those are all the outcomes. So it's not really just a number from 0 to 1. It's just going to be 1. And it's associated to what event? The event is really just the whole sample space with all the outcomes in it. And that's just saying that the probability of doing something, of some outcome happening, has to be 1, because those are all the outcomes. The probability of this event happening or occurring has to be 1. And then one more thing that I accidentally skipped about this other example here, so let me squeeze it in here now, is that the number associated to rolling an even, aka the number associated to rolling or to the event 2, 4, 6, that number, you should be able to think about it as the probability that you roll a 2 plus the probability that you roll a 4 plus the probability that you roll a 6. And that's because the 2, 4, and the 6 individually as events, just a 2, just a 4, just a 6, those events are all disjoint from each other. So you should be able to add up. So intuitively, you would say something like 1/6 plus 1/6 plus 1/6 to get 1/2. And that's the probability of rolling an even. So we really want this additive property to happen, and we really want the probability of the sample space to be 1. Okay, so that's going to lead us to the definition that we're after. So we want to think about probability as a function. So a probability function, so we're going to call it capital P on, for now, we're going to deal with a finite sample space. So our sample spaces always have finitely many things in them. So a probability function is what? Well, it's a function, first of all, which means that it takes something in and spits something out in a very nice way. So it's a function. What does it take in? It takes in events. So you plug in an event, and what pops out of the function? Numbers, but not any old number, just the numbers in 0 to 1. So including 0 or 1 as well. So the probability function is just a function that turns events into numbers. That's what we were doing up here. But in addition, we want some nice rules to happen, which is that first something has to happen when you do the experiment. And so that's saying that the event sigma, when you plug that in to the probability function, so this is how it looks when you plug something in, that better always be 1, because you've listed all the outcomes. So the probability of at least one outcome happening has to be 1 when you do the experiment, and this event has all the outcomes. So its probability has to be 1. And 2, if you have 2 events that are disjoint, like rolling a 2 or rolling a 4, they're disjoint events, they have no intersection, then you should be able to calculate, well, first let me just write it like this as well. This is the empty set. Then you should be able to calculate the probability of doing one of them or the other, like rolling a 2 or a 4 or a 6, by just adding up the probabilities individually. And that's what this is saying. So this is saying probability of event A or B occurring. So the keyword here is or is very much like a union. This or that happening is the same as just doing the probability of A plus the probability of B occurring separately. But this only needs to happen if the 2 things are disjoint. So this matches this example here that I was doing. So if I want to calculate the probability of rolling a 2, 4, or 6, I should be able to do independently. So this is like 2, 4, or 6 all in one set. I should be able to do a 2, a 4, and then I didn't do a third one here, but I should be able to do that separately. Because when I split them up, the events are disjoint from each other. Okay, so then just some more notation. So that's what a probability function is. But for an event A in the sample space, this number, remember this is a function turning events into numbers. So this thing is the function with an event plugged in. So this is going to be a number. Plugged into the function. So this number has a name. It's called the probability that A occurs. Maybe I'll underline the whole thing. Okay. So let's use this definition in some examples to sort of get a hang of it. Won't be so bad, I don't think. All right, so we need an experiment. So let's just flip a dice, and then we need a sample space, which is heads or tails. So then I can define P, a function on this sample space, by saying what it does to every possible event. So what are the events? Well, there's going to be 4 of them, actually. It's kind of tricky. So there's going to be 4 of these. So what are the 4 possible events from the sample space? Well, you could have the event where you flip a head. You could have the event where you flip a tail. So remember, events are just subsets. So I'm really listing all possible subsets. You could have the event where you flip a heads or a tails, which is really just omega. So that's got to be 1 for this to work. But the last one is the tricky one. So the subset that people forget is the empty set. The empty set is a subset of all sets, but it's sort of this tricky one. And you learn a bit more about this concept in set theory class, but we're just going to sort of gloss over it. That's because this probability will always just be 0. And you can think about it as like the probability that none of the outcomes happen is going to be 0 because one of the outcomes has to happen, because that's just how the experiment is working. Okay, so let's make this be a half so that it's like a real coin, this be a half, and then this has to be 1. So this is a probability function for this sample space. And then we can sort of just check the rules. So yes, the first rule is obeyed by definition. We just made that be 1. The second rule, it's actually really hard to check because you would have to check every possible pair of events that are disjoint from each other. So let's just check one thing. So let's do this one. So H and T, heads or tails, those are disjoint. So I better get the same thing as if I just add them up independently, which is what this is going to be. So let's see, do I get the same thing? Well, what is the bottom one? That's going to be a half plus a half, which is 1. And this, well, when I union them together, I just put them in the same set. And that is just this guy. So yes, I get 1 in either case. So it is true for those two, but in reality, you would need to check the second rule, meaning this one up here, for all possible disjoint events. And it could take you a while. So all pairs of disjoint events. And we just checked it for 2. It wouldn't actually take that long for this example, but for bigger examples, it would take very long to check all the possibilities. But luckily, we're not going to have to do that, and we'll see why in a second. Okay, so let's define another probability function for the same sample space. So it doesn't have to be a fair coin. We can define P by, so what we're going to do is just pick your favorite number, and we call it little lowercase p, and that'll be the probability of landing on heads. And then the probability of landing on tails will have to be something very particular to make it work. It'll have to be 1 minus that number, because then rule 1 will work. Because now if I do these added together, I'll get p plus 1 minus p is 1, which has to be p of the sample space. When I stick these two sets together, I get back the sample space ht. So this is another probability function. So you could pick this to be almost anything, but actually I got to be a little bit careful. P is just going to be the number, can be a number from 0 to 1. So P could be like 1/5, 3/10, 7/9, whatever you want. As long as it's between 0 and 1, then this will be a probability function. Okay. So yeah, just a reminder, this notation is saying P is a number from 0 to 1. And I'm not including 0 or 1, although I guess you could do that too, it'd still work. Okay, so let's see something that's not a probability function. So if I define heads to have probability 2/3 of occurring, and probability tails to also have 2/3 probability of occurring, then rule will break. One of the rules will break. If you try to make the other one work, then the other one will break. So for example, now if I do this calculation, if I do them separately, I'll get 4/3, which is not going to be 1, which is what I need it to be, because I need the probability of omega to always be 1. So in this case, rule 1 breaks. Okay, so this is not a probability function. All right. So just a quick note here. A probability function must be defined on all possible events of the sample space. And if you notice in these examples, I got a bit lazy. So I only said what happened to these two events, H or T independently, but I didn't say anything about what happened to this event or the empty set. And same thing here. And that's going to be for a reason, which is you can build the other ones from the smaller ones. That's going to be the idea here. Okay, so however, we can take advantage of the fact that an event A can be broken up into disjoint events consisting of one outcome each. And we can do this in order to define probability functions by just saying what the outcomes are assigned to. Sorry, what the outcomes get assigned to. Okay, so long paragraph, but we'll see some examples to make this more clear. Assigned to, sorry. So the idea is that if you have an event, I don't know, maybe it has like A, B, and C in it, you can always think of it as in pieces, just A union just B, just union just C, the set with one outcome each. And so then if you know the probabilities of A, B, and C separately, then you can calculate the probability of capital A using those three. That's going to be the idea. Okay, so let's do an example. So let's think about rolling a dice. 1, 2, 3, 4, 5, and 6 are the outcomes of the dice roll. So then it turns out there are actually quite a lot of events, 2 to the 6, which I think is 64 events. So if you tried to figure out all possible events, meaning all possible subsets, you would get 64 of them. So it would take a long time to define P of A for all events. So however, we're going to think about things the way I just said. So for example, if A is rolling an even, so it's got 2, 4, and 6 in it, then we can break it up into pieces like this, a union of 4 of 3 disjoint events, just rolling a 2, just rolling a 4, just rolling a 6. So these guys are disjoint. Okay, so if I do this, then if we just define the probability of A to be exactly what we want, meaning we just define it to be the probability of rolling a 2 plus the probability of rolling a 4 plus the probability of rolling a 6, and we know these 3 already, then we'll have probability of A. So if we define it this way, then the second rule holds automatically. We don't even have to check it because we defined the probability in such a way that the rule is enforced. So the second rule holds automatically. So let's do that. Okay, so we're going to define the probability function in this way. So we're just going to say the probability of each individual outcome as an event. And let's just make it a fair dice. So each one of them will be 1/6. Gotta write these annoying curly braces every time, but that's okay. So these will all be 1/6. Okay, so I'm just going to say what the probability of each outcome is as an event like this. And for any event A in the sample space, here's how we define its probability. So we're going to use fancy sum notation to get everything exactly the way we want it. So what we're going to say is that this should just be given by looking at the probability of each outcome and adding those up. That's what this is saying. So this is really just saying sum up probabilities of each outcome. So for example, if A is 2, 3, 4, 5, then this is saying this, you don't have to write it like I'm doing, I'm just trying to show you exactly what it means. So this is a summation symbol. So this is just saying add. And what is it saying to add? It's saying to add P of each event. I didn't make myself enough room. So I guess actually I'm missing one curly braces. So this should be the event consisting of one outcome each. So that's what this should be here. So this is saying, okay, X can be 2, 3, 4, and 5. So first I'll put in 2, then I add because it's a summation. Then I'll put in 3, because that's the next thing in the set. Then I'll add, and then I'll put the next thing in the set. So it's 4. And then I'll add, and I'll put the last thing in the set, which is the 5. So the probability of this event should just be given by 1/6 plus 1/6 plus 1/6 plus 1/6, which is 4/6. Okay, so then if I define the probability of every event in this way, which is just summing up the individual probabilities of each outcome as an event, then this is a probability function. Okay, so the second rule, this thing, where the events are disjoint, that's obeyed by definition. And here's how you can see that. So if A intersect B is disjoint, then what is this? Well, by definition of how I defined my probability of events, which is this thing, it's going to be this. So I just add up the probabilities of the individual outcomes in A union B. But because they're disjoint, there's no overlap. So I'm not double counting when I do them individually. When I do this, I'm just saying add up the probabilities for A and B independently. So this is just saying the probability of A you get by doing the probability of each outcome in A plus, and then the probability of B you get by doing the probability of each outcome in B, and then you can just put them together because there's no overlap, because this is the empty set. You can just do the x's in either A or B and add those up. But that's exactly what this is. That's this thing. So that's why this rule is automatically obeyed when you define probability of events by just doing probabilities of the individual outcomes added together. And then rule 1, which is that this guy needs to be equal to 1. And that's just because if I do the probability by adding up the probabilities of each individual outcome, the fact that I chose these originally to add up to 1 is what's going to make this happen. So if I just add up 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6, that will add up to 1. And so we can use this notation that I just wrote. But this is just saying probability of rolling a 1 plus probability roll a 2, and so on up until you get to the 6. And that's just going to be 1/6 plus 1/6 plus 1/6. 6 of these guys add up to 1. Okay, so this is a probability function. So we don't have to have a fair dice either. So the dice need not be fair as long as the total probability adds up to 1. So as long as, if I just go from 1 to 6, which is another way of saying what I just said, and I add that up to 1, so that's really the same as this guy. As long as this adds up to 1, then everything else you can change around. So what I'm saying is these don't need to all be 1/6. You can change them all around. As long as they add up to 1, it'll still be a probability function. But it's just a probability function of like some sort of weird dice that's unbalanced or something like that. Okay. So then, because of this trick, and laziness, I guess. You spell, I don't know how to spell laziness like that. Y or I, something like that. People tend to write, by people, I guess I mean mathematicians, they tend to write something like this instead of something like this, which is what you're technically supposed to write. So they just write it to mean the same thing because they get tired of writing all these extra curly braces. So 2 means the event 2 in this case. So we're going to follow this tradition from now on. Just to be annoying, I guess. I don't know. Okay. So just to summarize, and then we'll do another example. So probability functions have to have definitions for every event. You have to know where every event goes, what number every event goes to, but it suffices to define any probability function P on each outcome, instead of each event. And then you simply define it on events using this formula, which is you just sum up the probabilities of, of the outcomes in that event. So now I can just write X instead of curly brace X. And so then what happens is what I wrote before. When there's no intersection at all, you automatically get rule 2 to happen. You get that this is really this. And then that's the same as just adding up the probabilities for the outcomes in either X or B. But that's really just saying the union, because unioning is the same as saying the things in A or B. And then that's just the other side of the equation. Okay, so as long as we do that, and also we have to ensure that the total probability of all the outcomes better add up to 1, so that the probability of the sample space is 1. Okay, so let's do some more examples. Define P on, let's do a different sigma, I don't know, just have 3 things in it. And I can just say what the outcomes go to. But this guy is not a probability function because the total sum will not be 1. It'll be 1/3 plus 2/3 plus 1/2. Which I don't know what that is, but it's not 1. It's, I guess it's 1.5. So it's not a probability function. So let's say we have an unfair dice. And it's defined in this way. P is defined by rolling a 1, rolling a 2, rolling a 3, rolling a 4 will all have the same probability. And how about we make that be like 1/8? and probability of rolling a 5 and probability of rolling a 6 will be the same, and those will be 2/8. So this is a probability function. Because now these probabilities do add up to 1. If you do 1/8 plus 1/8 plus 1/8 plus 1/8 plus 2/8 plus 2/8, that will be 1. So then we can do things with this probability function, like ask, what's the probability of rolling an even with this dice? That's just saying, what's the probability of getting this event where you roll a 2, a 4, or a 6? And we just define it by adding up the probabilities of the outcomes in that event. So what are the outcomes in that event? A 2, a 4, or a 6. What's the probability of rolling a 2? Well, let's go up here. It's 1/8. Probability of rolling a 4 is also 1/8. Probability of rolling a 6 is 2/8. This will add up to 1/2. And then if we have event B is something else, I don't know, like roll a number greater than 2, then well, the probability of this event is going to be the probability of event 2, greater than 2. So you start at 3, 4, 5, or 6 being rolled. And again, same formula. We're just defining the probability function by the sum of the individual probabilities of each outcome. But I'm just going to keep writing the notation so you get familiar with it, but you can really skip this middle notation part that I'm writing. So this is probability of rolling a 3, a 4, or 5, or a 6 added together. And it's going to be 1/8 plus 1/8 plus 2/8 plus 2/8 for this weird dice. And so we get 6/8. So next time, we want to think about when things are not disjoint. Actually, that's going to be in 2 lectures from now. So let me just say later. Well, maybe it'll do a little bit on the next lecture too. But later, we'll think about probability. You know, I'm going to commit next time, actually. Okay, next time we'll think about probability when there is something in common. So this is not the empty set. Outcomes in common. So when they have things in common, you can't just do this anymore. It's going to be wrong. And that's because you're sort of going to be double counting for the things that are in the overlap. So just in this little example up here, so if I said, what's the probability of rolling an even or a number greater than 2, then that's really asking for, because of the word or, the probability of A union B for these 2 events I wrote up here. And I'm not just going to do 1/2 plus 6/8 or whatever, right? Because that's what this was, and this was 6/8. That would already be more than 1, which is bad. We can never get a number bigger than 1. So instead, what we're going to have to do is figure out how to deal with this situation. And what's really going on is they have overlap. So you sort of have to get rid of the overlap. Okay, so that's for next time. So See you then.